Hi everyone. I wanted to walk through how to do some of these wave math problems with you. So this is number 15 in the 5.1 Understanding Light packet. And you should have that packet as well as your electromagnetic spectrum handy so that you can reference the equations and the constants and formulas. So I'm going to show you that really briefly. So that's what this looks like. So I'm going to be using um, a couple of constants here down towards the bottom, as well as some formulas. And then we'll just be able to infer based on some of our answers what type of radiation. So I'm sort of going to use this sort of chart across the top to help us decide what type of radiation we're solving for here. All right, so let me go back to my problem. All right. So the first thing I wanted to do, and the reason we're walking through this in a video is because this is our first exposure to solving equations using algebraic manipulation in this class. And there are some tips that I am going to recommend to help reduce errors. So the first thing we're going to start with is just reading our problem, making sure we've written down our constants and everything is all written down. That's going to be the first strategy to help us reduce any errors. All right, so the first question here, this is number 15. Radiation is detected with a wavelength of 3.2 times 10 to the fifth nanometers. And it wants me to know what type of electromagnetic radiation this is. So I'm going to click back to this, and you can see here that this wavelength that's listed here along the top is in meters, and I'm given my data in nanometers. So the first thing I want to do is convert that value of wavelength from nanometers to meters. And I'm going to do that using dimensional analysis, knowing that a conversion factor, every 1 meter is equal to 10 to the ninth nanometers. And you can see here that the conversion factor, I've started with nanometers and I want to go to meters. So my meters unit is in the numerator and my nanometers is in the denominator so that I can cancel those out. So now I'm going to divide 3.2 times 10 to the fifth divided by 10 to the ninth. And my calculator broke, so I need to do that on my phone. So 3.2 to the fifth divided by 10 to the ninth. And that's giving me 3.2 times 10 to the minus 4. And my unit is meters. All right, so now I'm going to take that value, 3.2 times 10 to the minus 4, and I'm going to look at my electromagnetic spectrum. And I can see here that sort of in the 10 to the minus 4 area right here is an infrared wave. All right, so that is my answer. So this is A, and that's IR, infrared. And that is just a little bit longer wavelength than the visible spectrum. And we think about infrared as heat a lot of times. So that is a infrared wave. Now I want to know the associated energy for that wavelength. And so I'm going to keep my work in meters. I'm going to plug that in because my equation that I'm going to use to go from wavelength to energy, my constant c, the speed of light, is in meters. And so that's my second thing that I need to check is that the numbers that I'm plugging in are the same units of my constants. And since I just converted to meters now, I know that they are in the same units. So that's the one I'm going to use. All right, so I know that the formula that takes me directly from wavelength to energy is shown here. I wrote it down again, but it's also given in the equation. All right, so the second thing, my strategy here is to, when I write everything down, and I need to manipulate my formula in order to solve, I want to do that before I plug numbers in. Right? So I want to like solve for the unknown variable and then plug my numbers in. And here I know that I have two constants in the numerator and the wavelength in the denominator. So I really just need to plug those in and solve for E. I don't need to, you know, rearrange this equation in any way mathematically in order to solve for the unknown because I have a formula that gives me that. So now I'm going to write everything in here. 6.626 times 10 to the 34, and I always write units, times C, 3.00 times 10 to the 8 meters per second. I'm going to divide that by then this value that I solved for. All right, so you can see here that meters cancels. This sort of seconds comes, this one kind of comes to the denominator. So these ones cancel because that's a meters over seconds. And so I'm left with joules, which is the correct unit of energy that I'm solving for. All right, so I'm going to plug this into my phone. 6.626 to the 34th times 3 to the 8th. This should be minus 34. I'm just realizing there's a typo. All right, and then I'm going to divide that by 3.2 to the negative 4. So this is giving me 6.2119 times 10 to the minus 22. This is joules. And now I need to round to sig figs. So I'm starting with my given at 2. So my final answer needs to have 2 sig figs. So the energy of this wave is 6.2 times 10 to the minus 22 joules. And that's much less than what we would see perhaps if we were to calculate the energy of a visible wave, which is on the order of 10 to the minus 18 joules. So this makes sense that something with a longer wavelength in the infrared part of the spectrum would have less energy than a visible wave, which has a shorter wavelength. And that's how you do it.